Greetings. I hope everything's working okay and this is recording like it's supposed to be. My name is Dorian Janney, and I am going to be doing about a 45-minute webinar for you today and giving you an assignment that you can do for your course with Dr. Rajdev. So let me get started by opening up my PowerPoint presentation. And as I said, I'm going to be telling you a little bit about a NASA satellite mission, which is called the Global Precipitation Measurement Mission, and showing you a few other things as well. I am a former educator. I taught for over 30 years. I started off in the Frederick County, Maryland school system, where I taught, I ran the resource room back in the days when we used to have a pull-out model. And then I went to Montgomery County, where I taught for 30 years. And I started off actually also doing a resource room in an elementary school. Then I did a preschool special education program for many years. Moved up throughout all of the grade levels at the elementary level, doing both special ed and general ed, and then decided to go back to school to Johns Hopkins University and get a second master's in earth space science. So when I did that, back, I think it was probably about 1994 through maybe 98, then I started to do some work over at Goddard Space Flight Center in the summers with curriculum. And in 2011, I applied for and got a job as an educational specialist with the Global Precipitation Measurement Mission. Over time, then I retired from teaching, and over the past years, that job has kind of evolved, as many jobs are wont to do. Now I split my time between being the Global Precipitation Measurement Outreach and Communications Specialist, and I'm also the education lead for a GLOBE program that's called the Mission Mosquito Campaign, and I'll be telling you a little bit about that as well. These are the things that I would like to do today during this webinar. I want to introduce the Global Precipitation Measurement Mission to you, explain how and why NASA measures global precipitation from space, show you a variety of educational resources that are related to this mission, and share information on the GLOBE program and the GLOBE Mission Mosquito Campaign. So we're going to start off with looking at this satellite mission that I support that launched in 2014 and that measures global precipitation. So to understand the how and why we're measuring global precipitation, it's important to get an understanding of the differences between weather and climate. So weather is kind of like, do I use an umbrella today? What are the current conditions? And as you can see in the first graphic on the left, we're looking at conditions that are showing us that what's happening today, the temperature, the chance of precipitation, the wind. That's telling us the current state of the atmosphere. On the right, however, we're now looking at climate. And what climate is a lot more definitive than weather. Weather's based on so many moving parts, so many variables, that it is very hard to anticipate or predict what the weather is going to be like more than a few days ahead. Whereas climate is a series of mathematical averages. So with climate, it's fixed. We're not kind of guessing so much as we are taking usually the last 30 years, or depending on which kind of climate we're looking at. When we're speaking about current climate, we're usually taking the last 30 years and we're looking at the averages and using those averages to get a feel for what are the general patterns and trends. So in this case, when we're talking about an umbrella, with weather, we'll try to decide, do I need an umbrella today? Look out the window. Is it currently raining? Look at the forecast. With climate, it's kind of more like, do I have an umbrella in my closet? Is that something that I anticipate that I may need? The most notable changes of the most noticeable impacts of climate change will take place in our water cycle. Sometimes we think of it as being kind of the canary in the gold mine. The water cycle is a good way of trying to determine what some of the impacts are on our climate due to climate change. So in this case, when we're looking at water cycle, and I'll play this animation again, you probably remember, you probably taught this, we're talking about the way in which water moves throughout our water cycle. And so there are many, many applications for being able to measure how much it's raining and measuring how much it's raining and snowing. Measuring those over time using the same instrument, and then being able to compare and contrast this data and be able to better understand things like, are we going to have natural disasters like landslides? What is the impact on our agriculture? Do we have enough water for our agricultural needs? Things like being able to anticipate and predict floods, looking at hurricanes and better understanding hurricanes, which are the same thing as tropical cyclones. So these are some of the ways in which we're able to take the data that we do collect from a satellite like the Global Precipitation Measurement Mission, which I'll explain to you more about soon, and use those for these real-world applications. This is a video that explains, I'll move back to this, a little bit about.
Fortunately for us,
Earth's
we live
water.
on a water planet. But that doesn't mean we have an entire globe of H2O to use as we please. So just how does the usable water break down for us? A giant 97% of Earth's water is in the oceans, so we can't use that. 3% for fresh water, but even in that small sliver, 1.5% is locked in glaciers, ice caps, and in groundwater. That leaves less than 1% of the fresh water on Earth that is accessible and usable by humans. Let's imagine all of that accessible fresh water fits into this tiny pool. Now we'll get to some small numbers when we look at global freshwater. There really is a small fraction of usable and accessible freshwater on this water planet. So how do we use that tiny pool? In the United States, about 49%.
And I stopped it there because basically what I wanted to impress upon you right now is the importance of precipitation. What we were showing in that short video clip is that while we have a whole lot of water on Earth, we know that 73% of Earth's surface is covered with water, but most of that water is actually salt water. And to meet our needs, even to meet our energy needs, we rely on fresh water. So it turns out that less than 2.5% of all of Earth's water is actually fresh water. And most of that has traditionally been locked up in ice caps and glaciers or buried deep underground in the groundwater aquifers where it's very, very difficult to get to. However, we know that ice caps and glaciers around the world in many places are starting to melt. We also know that in many places, people are needing to dig wells deep into the aquifers and start to bring up that water and to be able to have fresh water to meet their needs. So one of the things that we're wondering as a global society is how is the melting of ice caps, how is the bringing up of those freshwater resources, how is all of that going to be impacting our precipitation? Is it going to have a noticeable effect? Now you might think, well, why are we measuring this from space when we have rain gauges all over the world that when it rains or snows, it rains into these gauges. We collect the rainwater and the snow, and we measure it, and we can see how much it's rained or snowed. Well, this animation shows us something that's very surprising. If you take all the rain gauges that we have around the world, and you were to bring them all together and put them in the kind of the same surface area, we would find that actually it equals less area than 2 basketball courts. Basically, what that means is that we are not getting a very good picture using our ground-based resources of how much precipitation is falling all over the world. In part, that's because when we have, mountains or places that are inaccessible, you can't really have a rain gauge there for somebody to go, or a snow gauge, and check on a regular basis and report in and empty it. The other thing is, we talked about the fact that 73% of Earth's surface is covered with water, and you can't effectively measure precipitation on the water. You don't have ships that are out there with rain gauges that are just sitting in place to be able to tell us exactly how much it's raining or snowing. So that is why we have satellite mission like the Global Precipitation Measurement Mission to be able to use a standard way of measuring, and to be able to do this from space so that we are getting this global picture. Now, as with most missions, they started somewhere. We didn't kind of just start with a global precipitation measurement mission and be able to measure precipitation all over the world. So in 1997, the Tropical Rainfall Measurement Mission, otherwise known as TRIM, was launched. This was, as is GPM, a joint mission for the US and Japan, and it was the first spaceborne precipitation radar. It set the standard for space for being able to observe and measure precipitation. And our data was used in a variety of different ways, including, of course, for research. And some of the applications were, as I mentioned before, natural hazards, agriculture, disease tracking. Another really neat thing that we were able to discover with the Tropical Rainfall Measurement Mission, if you look at the image on the right, you'll note here that we're looking at, and it might be a little hard to tell without knowing what we're looking at, but I'll explain to you. What we're seeing here is the different colors are showing us the intensity of the precipitation as it falls. On the right, we're actually looking at a hurricane or a tropical cyclone. And we note that these tall, red, we call them hot towers, although that is a misnomer, they're not actually hot, but these hot towers are actually showing us where there are these intense bands of very, very heavy precipitation that actually shoot way up into the troposphere. Because what we're able to do with this satellite mission is not only find out what kind of precipitation is currently falling from the clouds, but we're also able to get a 3-dimensional structure of how much precipitation is falling at any time in these different storm systems or from the different clouds. So we discovered these hot towers, which are not really hot, and that has helped us to better understand when tropical storms are intensifying and are gaining energy and becoming tropical cyclones or hurricanes by the presence of these hot towers. So that was something that was pretty neat that we were able to determine through our research from the Tropical Rainfall Measurement Mission. So this mission, like I say, it launched in 1997, and it was actually operational, gathering data, but only from the mid-latitude regions. But it did this through 2015. So we got a nice long record of precipitation. Now, as a result of having that very successful satellite mission, we then were able to use what we learned from that mission and then apply some new ways of using our satellite resources and bringing some other satellites in as well. And we launched the Global Precipitation Measurement Mission in February of 2014. And here's a short video giving you a little bit of information about that satellite mission.
Only 3% of water on Earth resides as fresh water, and only a tiny fraction of that is actually accessible to us on the surface.
7 billion of us live on this planet. We all have to drink water to live. Where's the water that we drink come from? By and large, precipitation.
GPM is an international satellite mission providing a new generation of observations of rain and snow in all parts of the world every 3 hours.
If you have good precipitation information, you can do a very good job of characterizing drought and often its subsequent impact on agricultural productivity.
There's about one major flood a day someplace in the world. So it's not as if it's a rare event.
Understanding how much snow is falling is important for transportation, safety, how much fresh water falls and is stored in snowpacks. But we really need to focus on all the phases of precipitation so that we know with a global picture of where fresh water exists in the Earth system.
And all of the videos that I'm showing you are available on the website that I'm going to be showing you as well. So here we have an animation of the Global Precipitation Measurement Mission, the one launched in 2014. And one of the instruments that we use is a radar. So in the same way that radar is used to be able to see if you're speeding on the highway, we can use radar to give us that three-dimensional data that we're looking at to be able to determine how much precipitation is falling in our storms. We also use the GMI, which is the GPM microwave imager, and we use microwaves to be able to determine, based on the reflectivity or absorption in the clouds, we're able to determine exactly what type of precipitation is falling from those clouds. So you see here we've got two types of radar on board. We've got what we call an active and a passive, so a KA and a KU and a KA band, and that again is, I'm missing an L there, is giving us the precipitation in kind of a three-dimensional structure. And we have that microwave imager, 13 channels, which are able to give us this integrated understanding of what type of precipitation. Is it rain, sleet, snow, freezing rain, so on and so forth. This is it doesn't have any music or words to it, so I'll talk through it. But what we're looking at here is, you notice from looking at the key at the bottom, again, we're talking about frequency, so we're talking about millimeters per hour. On the left, we're seeing liquid precipitation, so our green through our dark red scale is showing us the intensity. Green meaning less liquid precipitation, and red to the dark red meaning more. With the blues and the purples, we're able to also measure the frozen precipitation, which is something we didn't have the technology to do with the previous mission, with the TRIM mission. So now we're able to not only get the tropics, we're actually able to get a global representation because we do have other satellites working with us. So now I'm going to show you a short video that I think is really appropriate when you're working with students to show them, because it gives a pretty basic understanding of how and why we're able to use satellites in kind of an artful way to measure global precipitation.
We plan our lives around rain. We always want to know when and where and how much, not just for our weekend plans, but for how we make decisions about our safety and transportation, our economy, or our livelihoods. So, how do we measure rain? Well, we can set out a rain gauge, like this one, and it measures the amount of rain that falls over time. The problem with this is that it only measures rain in one very small spot. In fact, if you took all of the rain gauges in the world, packed them together, they would fit into 2 basketball courts. Now, we can cover more ground if we use radar. Radar sends out a signal, and it measures how much of that signal is scattered by rain or snow. But radars are only available in certain parts of the world, and many countries just don't have access to that technology. And that's just on land.
So I'm not sure why that did that. Let's come back and see if it can keep going.
We plan our lives around rain.
A little bit.
That are going to give us accurate precipitation rates for the whole globe. So we have to think bigger and higher. Instead of having a patchy network of rain gauges and radars, we could have a whole constellation of satellites looking down at the Earth, measuring things like falling rain, snow, and even ice. The Global Precipitation Measurement Mission, or GPM, is going to do that, and it's going to give us precipitation rates for the whole globe every 3 hours. Now, GPM is going to cover it all, from land and oceans, from the tropics to the edge of the poles, over mountains and valleys, from our farmland to our cities and towns. We're going to need more than a perspective on the ground if we're going to look at precipitation from a truly global standpoint. And GPM is just the mission that's going to give us that big picture.
And don't worry if you missed a little of that. I'm going to be showing you where you can access this video and others as well. Oops, we're going to skip through there. So as I said, we've got a couple of different ways in which we're able to be measuring this precipitation, and basically just two instruments. One of the activities that you may choose to do, because it's my understanding that you need to do an activity, a STEM activity that you're going to be doing yourself and then reporting into Dr. Rajdev about. So one of them, a possibility, is creating an edible model of GPM. And so you'd be showing on your model, and I'll give you some more information in a little bit, what the satellite looks like, and showing the solar panels that you see there, in addition to your microwave and your radar instruments. Another really cool thing about several NASA satellite missions, but in particular the GPM mission, is that we do rely on gathering data from some other satellites that are up in orbit studying other things to be able to give us that global picture. So the GPM Core Observatory is the main observatory. TRMM, the TRMM satellite mission, was in operation for 1 year while GPM was in operation. It was decommissioned in 2015 because it was running out of fuel and getting old. But then you'll see there are some other satellites that are up, and you'll notice that some of them are from other countries. Those satellites happen to have microwave instruments on board. So we're able to take the channels that we need, gather that data, put it through our core processor, and then use that data to get an updated picture of how much precipitation is falling all over the globe, and we update that every 3 hours. Pretty amazing when you think of the technology involved. This is going to show us some swaths. So here we have our GPM. We go around Earth about 16 times a day, fairly common. We're about 250 miles above Earth. But you see with these other satellite missions that are also going around Earth, when we pull all of their swaths together, what we see is that every 3 hours, we get this complete measurement, this complete picture of how much precipitation is falling all over the globe. Now I'm going to make it kind of, now I'm going to show you how, a video that explains how NASA satellites are able to do this remote sensing. It's called the data downpour.
The GPM mission is a sophisticated network of satellites covering the entire globe in less than 3 hours, giving us an unprecedented picture of precipitation from rain, falling snow, hurricanes, monsoons, droughts, and floods. So how do we get all of that information out of this? The short answer, tons of data from all over. As GPM takes snapshots of precipitation, like in a major storm, the data gathered is transmitted to a network of satellites called TDRS.
The important thing to recognize is that the GPM satellite doesn't talk directly to the Earth. It talks to the communications satellite, which is known as TDRS. And TDRS satellites talk to a ground station, which is at White Sands, New Mexico. And that's a very effective way to get continuous data, which cannot be gotten otherwise, unless you do direct broadcasts and have many, many ground stations, which isn't as effective as going through the TDRS system.
The White Sands ground station then sends information about the health and geolocation of the GPM core satellite to the hub of all of this activity, the Missions Operations Center, located at NASA's Goddard Space Flight Center. The raw data streams into Goddard's Precipitation Processing System, or PPS. The data from the radar is routed through GPM's partner, the Japan Aerospace Exploration Agency, for initial processing, and then is sent back to the PPS.
The data that come down from the satellite are actually not precipitation. They're in the form of radiances in the case of the microwave instruments, or reflectivities in the case of the radar. The computer codes I've been talking about, the algorithms, are the way we get from numbers that nobody, including me, can directly interpret to the thing that we care about, which is precipitation.
The GPM mission is not just the core spacecraft, but also a constellation of existing satellites from partners around the world. Each constellation member may have its own unique scientific objectives. They all contribute data to the PPS in order to develop global precipitation products.
Precipitation processing system gets data from the satellite and various other sources and creates the science products that are going to be used for both applications purposes, that is societal benefits, and scientific research.
The PPS then produces a suite of data products, including both instrument-specific and merged data, unifying the data gathered by the international partner satellites that make up the GPM constellation.
You could compare this to making soup. We have carrots, and we have onions, and we have potatoes. They're all vegetables. And so you have to wash them, peel them, take out the bad spots. That's a really important step. You don't want your soup to taste bad. When you get done, of course, you have to taste test it to make sure you have the seasoning right, and then you have to serve it. And so each of those steps, in a mathematical sense, is what we have to do in order to take all the diverse sources of information and end up with a unified product, which the user finds to be useful.
These precipitation products will be useful in many societal applications: hydrologic modeling, mapping potential natural disasters, agricultural monitoring, weather prediction, and climate research.
As we improve the precipitation retrievals that form the basis for these merged products, that will get better and better, and we'll be seeing actual satellite data rather than just forecasts.
That may be, well, that information is probably more technical than one would need to get into if you're dealing with elementary school students. But I think it does a really good job of explaining how it is that we're able to gather these reflectances and absorptions and bring together the mathematics. So we take the technology, we bring together the mathematics, and from that, we're able to come up with what we call these algorithms, these models. Then, of course, we have to do an awful lot of ground truthing to make sure that what the models are showing is exactly the same as what's actually happening at the ground level. And we have had over 10 of those different ground truthing experiments that have taken place. And I'll show you where you can access the information on that as well. What I want to show you now, I think, is super cool. And this is something that you can access for every single week. It'll start with the day that you access the data, and it will go back for a week in time. So what this is showing us is this, or at least from when I've done this, and today is the 22nd, you'll probably be looking at this next week, but this will show you what the precipitation measurements were for last week. So this is starting with January 15th. You'll notice the time and date stamp over there on the left-hand side. That is using universal time, so which also sometimes is known as Greenwich Mean Time. And then you'll notice down at the bottom, we see those keys for the liquid and the frozen precipitation. I want you to notice too, this is something I think is so fascinating with our data. As you watch the precipitation and as it's moving across the world, you'll see that at the upper latitude and the lower latitude, our wind patterns are moving in a west to east direction. Those are our global wind patterns, and certainly we see that here. It's also pretty cool that you can see then at the equator, we're seeing then that the wind is actually kind of working as a conveyor belt, just like we've read is happening, but here we're actually seeing that this is indeed what is happening as we're looking at precipitation. So we're seeing that in the northern and southern hemispheres, the precipitation and the wind is blowing, moving from west to east, and then at the equator, it's moving from east to west. So pretty fascinating stuff. I know that for us over here on the East Coast, so jumped ahead, we have been, no, I don't want that. We have been experiencing a lot of precipitation, and now it's moved off, and that's exactly what we're seeing. So pretty neat information. There are many applications for the GPM satellite data and the TRIM data as well. Now we've got over a 30-year record using these instruments, looking at the amount of precipitation to the millimeter level that's falling. With the TRIM mission, of course, we were just looking around the equator in the mid-latitudes, 33 north to 33 south, whereas now with the GPM mission since 2014, we have been able to measure actually almost up to the North Pole, so about 66.5 north to 66.5 south, which gives us just about global coverage. And this helps us to be able to better understand, of course, things like flooding and landslides, to be able to do some of these climatic modeling and land surface modeling and get a feel for being able to predict what we think is going to happen in the future based on mathematical averages, know about freshwater availability, where and when people will have access to fresh drinking water. Again, those extreme events such as flooding help us with knowing when conditions are right for agriculture and when also we need to have some early warnings for famine. Knowing that the agriculture and there's not enough water, drought conditions are taking place, and that we could start to see some breakdowns with agriculture. Another huge application, and one that I was focused on last year, and I'm continuing to be working on with the GLOW program, which I'm going to tell you more about in a minute, is with World Health. And we're able to predict, monitor, and respond to many different types of diseases and health conditions because so many of those are based on either too much precipitation or not enough. So now I'm going to take you, hopefully this will work like I want it to a couple of different pages to show you some resources. This is called Precipitation Education, and this was a website that was put together back when we had a lot of emphasis on education. And what you're going to find here, this is all made for students and for teachers, and you're going to learn a lot about why do we measure rain and snow, the things that I was explaining to you a little bit earlier in the webcast. You're going to see some of our more current resources that you can access, giving you more information about some of the different ways in which you can learn about and utilize this information. I also want to draw your attention to the fact that we have 4 key themes. We've got the water cycle that is easy to pull out of the science, technology, and engineering and mathematics for this satellite mission. We also have weather and climate, technology, and societal applications. So each of those, if you click there, then that's going to take you to a new page where you're going to see some of the resources either that we have created or that we pulled together that are based on better understanding that technology. You'll also see that we've got career information here, things on articles, which means it's a one-page front and back for students and adults to read and get a better understanding of how and why, say we read rain gauges, how we're able to do that. So here you've got a variety of different types of activities, be they lesson plans and other ways in which you can learn more and teach more about this mission. Something I would suggest doing is from our homepage is doing this short, I think it's about a 3-minute video tour, which is going to show you how to access the different resources on our website. So that is something that I would suggest you take some time to do, and will help you to know what some of these resources are that you can be using with your students. We also have, let me go to, I'm clicking on GPM Original. Here I'm going to say lesson plans and say apply. For our lesson plans, we have teacher guides, we have student capture sheets, some of them have pre and post assessments. And for any of our GPM original lesson plans, we will also provide you with answer keys. You come down to the bottom here, where is it? Somewhere here we have where if you want the answer key, let me go to one of our lessons. I'm going to go to this one here. And let's say you want the answer key, you just do the contact us. And then here you're going to give us your name, your school, your email address. You're going to write in the subject. It's very helpful if you say which lesson plan you're looking for you want the answer key for. So here you might say precipitation towers. And then if you have a message, you can send that to me. And then there'll be a security question just to ensure that you're not a robot. And then you do submit, and then those come to me, and I am able to send you pretty quickly the answer key for our GPM original lessons. I also wanted to show you the GPM mission webpage, because this is where you're going to be able to see the latest data that we've been collecting. You could learn more about the TRIM mission or the GPM mission. You'll be able to come here and see where it says latest half hour. This was for the last half hour data that was collected today. And if you want to see the most recent animation for the past 7 days, you'll just click there. And that's where you're able to see the most recent data from our satellite. So pretty cool stuff. All right, I told you there's 2 different things that you can pick from to do your activity that you need to do for this class. One of them can be the Rain Gauge Design Challenge. So this is one that we developed, and with this one, what you're basically going to be doing, and let me see if I open this up, you're going to be taking some different types of potential containers that you could use to measure precipitation. And with the students, excuse me, we like to offer them a lot of different choices, because that gives them kind of an engineering challenge to be working with. They have these different choices to work with. They pick which of these they want to make their rain gauge for. We do not tell them how to do it, because we want this to be an engineering challenge where they're thinking through, trying to decide, well, when we measure precipitation, is that actually measuring cubic milliliters or cubic centimeters, or is that measuring the height of the precipitation? We want them to be considering the possibilities. So in this case, we have some different measurement tools that they can be using. Then they take the rain gauge that they've designed, and what we often do is we'll take them outside and we'll just pour water into them using kind of like a little watering can, and then we'll have them compare and contrast how their rain gauges differed. And then they can also talk about what do they feel are the best practices for making these rain gauges. And here you can see some pictures of some students doing that. So that's a really fun challenge that you can work with, and that works very, very well with both student and adult groups. And then another one that's kind of fun to do is this edible model of GPM. So here in this case, you can see that what we do is we keep the picture of GPM up, or maybe you have it on a projector, you show them what it looks like. You're having them really pay attention to the different parts of the satellite. And in this case, they're developing a model where they're showing these different parts of the satellite using something that they can eat, which is, of course, a real good primary reinforcer to have things that you can eat. There is a more healthy example of this done by, surprisingly enough, someone in California came up with a healthy one that involved even using seaweed on the solar panels. So fascinating to see what different things people come up with. I also wanted to show you, if you want to get the data, and I was showing you that GPM page, this gives you a little more specific information on the types of data that you can get. All of our data is freely accessible. Some of it is rather complicated, so you probably are going to need to be understanding the algorithms and understand how to utilize the data in a more complex way. However, you can see those 7-day iMerge, which means we're bringing together a lot of the GPM data and some ground resources as well to give us that one kind of complete picture. Of course, we're on social media. You can follow us with Facebook. There's lots of videos that you can find that are focused on GPM, and of course, our education site. I am going to go ahead and stop there because I have to get to another meeting. And at another time, if you're interested, I can give you more information on the GLOBE program info. So I hope that you've learned a lot from this. I hope this is useful, and have a lovely day. Look forward to having you use our resources, and let me know should you have any questions.